Okay, so our next talk will be by Michael Hofstetter, also from Cambridge, and Michael will tell us about the maximum encoupling of the sine-Gordon field.
Yeah, thank you very much, and hello to everyone who is attending this talk. It's a great pleasure to speak to you today. And in this talk, I will present a project that I did together with Roland, who is my PhD supervisor. And this project emerged from my interest in extremal processes and extreme values of Gaussian and non-Gaussian fields, and Roland's interest on the sine-Gordon field. So the structure of this talk is going to be as follows. So first I will introduce the setting. Then I will briefly review existing results in this area, which are particularly important to us as they gave us a motivation for the results that we try to prove. Then I will present the main result, which is going to be convergence in law for the centered maximum of the sine-Gordon field. And then I will present a strong multi-scale coupling that Roland mentioned just a couple of minutes ago between the discrete Gaussian free field and the sine-Gordon field, which is a very important result and which is interesting and of independent interest, and which allowed us to answer the question on the limiting distribution of the maximum for the sine-Gordon field. And in the last two sections, I will explain how we can use this coupling to connect to an existing proof in the literature, which is for convergence in law of the maximum of the discrete Gaussian free field. Okay, so the setting here is very easy, and it is as follows. So we take the discretized unit torus, which is the continuum torus, and we intersect this torus with a grid of mesh size epsilon. And then we consider functions from this discretized unit torus to the real values. So we think of these functions as discretized surfaces or height functions. And then we take a probability measure nu epsilon on this set of discretized surfaces. And then we take a random variable which takes values in this set of surfaces. And the law of this random variable is given by the probability measure nu. So here are two pictures how we can think of these objects. So on the left-hand side, we have the discretized torus, and we assign to each vertex a real number. And we do this in such a way that the law, well, and then we consider this random object, which is given by this phi epsilon, which has the law nu epsilon. And so on the right-hand side, we see a typical configuration for the field. So we see one sample of this probability distribution. By the way, I should also say, if you have any questions and if you feel that I didn't explain something sufficiently well, then you should feel free to interrupt me at any point, and I will try to give further explanations. Okay, so here's a few examples. The most important and most fundamental example which falls into this setting is the discrete Gaussian free field, where the probability distribution has the following density. So this is given by e to the minus this quadratic term, and here this discrete Laplacian is given, of course, by summing up the differences over all nearest neighbors. And we also have, since we are in the torus, we also have a mass term, and here the mass is for convenience set to 1. The reason why this is called discrete Gaussian free field is, of course, because we can, because this density is in fact a multivariate normal distribution, and the covariance matrix of that multivariate normal distribution is given by the inverse of the discrete Laplacian plus the mass term. The next probability density, the next model that is interesting for us is the Sine-Gordon field, which also falls in this category. And in this case, as we have seen before, the probability density is given by this this modified exponential term. So in the exponent, we have again this quadratic term, which is the same as in the case of the Gaussian free field. Plus, we have an additional term which is given by the sum over all these cosine terms. So this additional potential was denoted V in the talk before, or V0 if you want. Let me also mention the Ginsburg-Landau gradient interface model, which also falls in this category. In this case, the density is given similarly, but we have a more general potential here, which is now symmetric and strictly convex. And the reason why this is called gradient interface model is because this potential is in fact a function of the discrete gradient. So here the assumptions are strict convexity, even though the strict convexity can be further relaxed to just convexity in some cases. Let me also mention that both the Sine-Gordon field and the Ginsburg-Landau gradient interface model are well, the discrete Gaussian free field is a special case of both the Sine-Gordon field and the Ginsburg-Landau interface model, and this can be seen, for instance, by choosing this coupling constant Z here to 0, in which case we recover the density of the discrete Gaussian free field. And in the second case, by choosing this potential to be the quadratic potential, we again recover the density of the discrete Gaussian free field. So the difference between these two models here, the Sine-Gordon field and the Ginsburg-Landau interface model, is this additional term that we denoted V in the previous talk, this additional periodic and local potential that we add here, makes the Sine-Gordon field look like the discrete Gaussian free field on small scales, but not on large scales. And the Ginsburg-Landau gradient interface model looks like the Gaussian free field on large scales, but not on small scales. So this is somehow the difference between the second and the third model. Also, let me emphasize that the Sine-Gordon field is a non-Gaussian field, and also the Ginsburg-Landau field is, of course, a non-Gaussian field. In fact, this parameter epsilon that we have here can be seen as a regularization parameter, and it is known, and it is absolutely not obvious, that when we take this regularization parameter to 0, then these three models have a continuum limit, and in fact, this continuum limit cannot be thought of as a random height function, but rather as a random distribution, which takes values in the space of Schwarz distributions. For instance, in the first case, the limiting object is called the continuum Gaussian free field. In the second case, it's the continuum Sine-Gordon field, which I emphasize again is a non-Gaussian distribution, a non-Gaussian Schwarz distribution. And in the third case, the limiting object is again a multiple of the continuum Gaussian free field. Okay, and so if we want to test this limiting object, we need to, of course, evaluate it at sufficiently smooth functions. So we integrate it against smooth function. And so one question that is not covered by this is our non-linear properties and non-local properties, such as the maximum of the field. And of course, it's not possible to define the maximum for a distribution, as this is not defined, as a distribution is not defined pointwise, but we can, so having this regularization in place, we can define the maximum for each regularization. And then, so this is now a well-defined object, as we take the maximum only over a finite set of points. And then we can ask questions about how does this object behave as this regularization parameter tends to 0. And then the natural questions are, what can we say about the expectation value? Do we have tightness for the sequence of centered maxima? And if so, would we also have convergence in distribution? So these are very, very important questions here. Further questions are, can we say anything about the extremal process, or what can be said about the level sets of the field? Okay, so let me now give a brief survey on existing results in the literature. So in general, there's also a lot of results on, for instance, branching random walks and random matrix theory, where the maximum is an interesting object to study. But in this review, I will only mention results where an underlying lattice structure is present. And so these results can be grouped into two different categories. So the first one is our Gaussian results, so results for Gaussian fields, and the second one are results for non-Gaussian fields. And in general, one can say that in the case of Gaussian fields, much more is established and known, since there is since there is very important tools such as comparison inequalities for the maximum, which a priori do not hold in the non-Gaussian context. The first result in the Gaussian case is the very important result by Bramson and Saltuni, which is a result for the discrete Gaussian free field. And in this paper, they identified the first and the second order of the expectation value of the maximum, which is given here by a logarithmic term in the first order and a double logarithmic term in the second order. And this constant g here was found to be 2 over pi. And in this paper, they also obtained tightness for the sequence of centered maxima. So centering is here with this constant m epsilon. So this I abbreviated this constant here as m epsilon, and this will be important as well in the rest of the talk. So once we have tightness for the sequence, the next logical question is then, do we also have convergence in law? And so the answer is yes. Bramson, Ding, and Saltuni managed to establish this convergence, and they found that, again, for the discrete Gaussian free field in 2 dimensions, this sequence of centered maxima converges in law to what is called a randomly shifted Gumbel distribution. Then Ding, Roy, and Saltuni were able to generalize this to arbitrary log correlated fields. So log correlated fields are fields where there is a logarithmic divergence in the correlation function. So this result is, of course, a generalization of the previous result by Bramson, Ding, Saltuni for the discrete Gaussian free field. There's also another group who obtained results on the discrete Gaussian free field, which was Biscop and Louis-Dore. And they had a look at, again, so they were also interested in questions on the discrete Gaussian free field, and they had a look at what is called intermediate level sets, which are random sets of this form. So here, this is the set where the random set of points where the field attains high values, and they were able to prove results on the size and geometry of this level set. So, for instance, what can we say about the number of points that we see in this level set, and where are these points located on the field? And they also gave a characterization of the full extremal process, again for the discrete Gaussian free field in 2 dimensions. In the non-Gaussian case, as I said, much less is known and fewer results have been established. And here, let me mention the result by Belius and Wu, where they found that the first order of this expectation value here, in case of the Ginsburg-Landau gradient interface model, is also given by a logarithmic term, and they also identified this constant here, which is of course not the same as in the case of the Gaussian free field. So it is believed that it is believed that this constant here depends on the small scales of the field, and so this is not a surprise that this constant now looks different in the case of the Ginsburg-Landau gradient interface model. Okay, then another result again on the Ginsburg-Landau gradient interface model is this has established in the paper by Wu and Zaitouni, where they obtained the subsequential tightness for the sequence of centered maxima for the Ginsburg-Landau interface model. Let me also mention a result by Wirth, where he had a look at the maximum of the so-called integer valued Gaussian free field, which is similarly defined as the Gaussian free field, but where the field is only allowed to attain integer values. Okay. So let me now present our main result, which is a convergence in law for the maximum of the Sine-Gordon field. So let's take again this this random variable which has law given by the Sine-Gordon measure, and here I'd like to emphasize this again. We have this Gaussian term plus a periodic potential, which is the sum over these cosine terms. And the theorem now is as follows. So for beta in 0 to 6 pi, remember beta is the parameter that comes with the Sine-Gordon field and which is allowed to be in the interval 0 to 8 pi. So up to 6 pi, we have the following convergence result. So the centered maximum, the centered maximum of the Sine-Gordon field converges in law to a randomly shifted Gumbel distribution. So this is, let me emphasize that this is the analogous result for the Sine-Gordon field, and this has been established for the discrete Gaussian free field and for general law correlated fields. And but in this case, the important remark here is that the Sine-Gordon field is of course a non-Gaussian field, and it has also a non-Gaussian limit. So this is a result for a non-Gaussian field, whereas in this result has been mostly established for the Gaussian case. Okay, so let me make a few remarks on this theorem. So first of all, the constant m epsilon here that we subtract to center the maximum of the field is actually the same constant as in the case of the discrete Gaussian free field. The prefactor here is, however, a bit different, but that only depends on how the field is scaled. So that means how the variance scales and what the prefactor of this variance at a point is. And if we scaled, of course, the field as it is scaled in the corresponding result for the discrete Gaussian free field, we would see the very same constant. Then let me also explain what a randomly shifted Gumbel distribution is, as this is a non-standard distribution. So first of all, a Gumbel distribution is a distribution which is supported on the real line and which has the following distribution function. So here we see this double exponential form, and it's easy to check if we send, for instance, x to plus infinity, then this converges to 1. And if we send x to minus infinity, this converges to 0, which makes this a distribution function. And a random variable which has this distribution function is called a shifted Gumbel distribution. So here the shift mu appears here in the second exponent. So what does it now mean to be a randomly shifted Gumbel distribution? So the random shift means that the shift that appeared here in the second exponent is also a random variable, which is independent of the Gumbel random variable. And here above, so let me also emphasize that we see this randomly shifted Gumbel here on the right-hand side, and as I mentioned, the term that we subtract is the same as in the case of the discrete Gaussian free field, but the difference here is apparent in this random shift. So this random shift is different to the corresponding random variable in the discrete Gaussian free field, and which is in this random variable we see the influence of this additional sine-Gordon term. Okay, so let me now present our most important tool, which I said already is of independent interest, and which is a strong multi-scale coupling between the sine-Gordon field and the discrete Gaussian free field. So as a motivation, we start with what we call the decomposed discrete Gaussian free field. So we take again this matrix C dot, which is given by the exponential of the Laplacian. So in other words, this is just a heat kernel, and we take a Brownian motion of the right dimension. So here the dimension of this Brownian motion is increases when we take epsilon to 0. And of course, when we think of this heat kernel as a matrix, then this matrix gets more and more high dimensional. And then we define the decomposed discrete Gaussian free field as the following stochastic integral. So we take this this heat kernel and integrate it against the Brownian motion, and we integrate this from t to infinity. And we also I should emphasize that we think of this process as starting from infinity and going down all the way to 0. Okay, so why is it called decomposed discrete Gaussian free field? So first of all, just by construction as a stochastic integral with respect to Brownian motion, this is always a mean zero Gaussian field with covariance matrix given by integrating the square of the heat kernel, well, the heat kernel itself, as we had the square root here. So this is just given by integrating the heat kernel from t to infinity. And so when we go down all the way to 0, so we actually recover the massive discrete Gaussian free field, which is a Gaussian field with the following covariance matrix. So this is the reason why this is called the decomposed discrete Gaussian free field. And so what Roland emphasized already, we shouldn't think of this parameter t, this index t, as a time parameter, but rather as a scale parameter. So here is two pictures which we have in mind when we think of this scale. So on the left-hand side, we see a typical sample of the decomposed discrete Gaussian free field for large scales. So on large scales, we have very, for the scale index to be large, we only see fluctuations on large scales. And the further we go down to 0, the more fluctuations we accumulate on small scales. And eventually, when we go down all the way to 0, we end up with an object that has fluctuations on all scales, and which is then the discrete Gaussian free field. Okay, so this decomposed discrete Gaussian free field served as an introduction for or as a motivation for this coupling result, because the question is now, can we have a similar result for the sine-Gordon field? So can we also decompose the sine-Gordon field? And the answer is yes. So we can do it in the following very convenient and nice way. So we fix some epsilon, and then so the statement is as follows. So there's a unique process phi SG epsilon, which I refer to as the decomposed sign-Gordon field, which also takes values in the set of discrete height functions or discrete surfaces, and which is adapted to the backward filtration of W. So remember, W is the Brownian motion that we use to construct this decomposed discrete Gaussian free field. And then we have the following very nice coupling results. So the decomposed sign-Gordon field is equal to the decomposed Gaussian free field plus some difference term. And of course, so in the case of the discrete, of the decomposed Gaussian free field, when we go down all the way to 0, we recover the discrete Gaussian free field. And here, the statement is similar. When we go down all the way to 0, then we end up with a random variable which has the same, which has the distribution of the sign-Gordon measure. So which has the distribution that we're interested in. Okay, and you know, the interesting questions and the most important questions here are, of course, what can we say about this difference term? And the somehow remarkable properties are as follows. So first, this difference term phi delta is uniformly bounded in the scale parameter and, more importantly, in the regularization parameter epsilon. Second, so when we have a look at this this difference parameter, we can say that the difference between this field phi delta at t and phi delta at 0 converges to 0 uniformly in epsilon, and the emphasis is here uniformly in epsilon as t converges to 0. And additionally, this difference field phi is Hölder continuous again uniformly in epsilon. So so we have this very nice coupling result which says that the sign-Gordon field and the discrete Gaussian free field can be realized in the same probability space up to a function which is which has very nice properties. So finally, there is also a independent statement contained in this coupling. So in the case of the discrete Gaussian free field, we had independence of large scales from small scales, but here we cannot expect the same, as the field is now non-Gaussian. But we still have independence of large scales of the sign-Gordon, of the decomposed sign-Gordon field, from independence of small scales of the discrete Gaussian free field. Okay, let me rephrase the statement again. So in words, this means that the decomposed discrete Gaussian free field and the decomposed sign-Gordon field can be coupled. So that means realized in the same probability space up to a random Hölder continuous function, which is moreover uniformly bounded. And uniform means, in fact, uniform in this regularization parameter epsilon. So above, I stated this result for epsilon strictly positive, but in fact, since the bounds we obtain are uniform in epsilon, we can take the limit epsilon epsilon to 0. And in that case, of course, we for t equals 0, we don't, so we have the entire sign-Gordon field. And in this case, convergence is not towards a random height function, but rather in the space of distribution. So we need we need to consider the space of distributions here. And but for every t which is strictly positive, we actually have convergence to a smooth surface. So a field that takes values in the space C infinity, in the space of smooth functions on the torus. So another important remark, so before you actually want to identify the limiting distribution, you should convince yourself that, for instance, the sequence is tight, the sequence of the centered maxima, and also you should know what the first and the second order of this expectation value is. But in this case, the coupling gives a very significant shortcut to translate these, well, a shortcut that allows to translate these two properties immediately from the discrete Gaussian free field. Okay, so here is an additional picture to further explain this coupling result. So, so again, I want to emphasize that we think of these processes as processes starting from infinity, so at large scale, and going down to 0. And the statement says that we have, so we have pointwise equality on each scale. And so if we fix one scale, we have that the large scales of the sine-Gordon field, which are shown as a red bar here, the large scales of the sine-Gordon field are independent of the small scales of the discrete Gaussian free field. And moreover, we have an additional difference term phi delta, which can be made uniformly small when taking this parameter t to 0. So this will later allow to find a very useful decomposition and to get rid of this difference term, which destroys independence in case of the sine-Gordon field. Okay, so here is in this slide I want to sketch the proof of this coupling result, and so so we take again this renormalized potential, which is given by this Gaussian expectation value. So here the expectation is this zeta is the variable which which we integrate out here with respect to this Gaussian measure, and the covariance function of this Gaussian measure is given by the integral of the heat kernel. And then we construct the solution. We construct the decomposed sine-Gordon field as a solution of the following SDE. So here, so this equation was already in the last slide of Roland's talk, and we see that on the right-hand side we recover the decomposed discrete Gaussian free field again, and so consequently this term in the middle here has to be the difference term, which we denoted as phi delta. So a very important property which makes this decomposed sine-Gordon field work is the fact that at 0 we recover the density of the sine-Gordon field, and this can be seen using Ito's formula and this evolution of and the Polchinski semigroup and the evolution of the renormalized measure. So by Ito's formula and the fact that V, this potential, this renormalized potential satisfies the Polchinski semigroup, it can be shown that in fact the field phi 0 has the distribution of the sine-Gordon field. Okay, and so the interesting questions are now, what can we say about this difference term? And so in fact we can bound this difference term uniformly in epsilon, and moreover by a deterministic constant, which is rather surprising. So in the first step we can take the maximum inside, and then we're left with a random object here. And I'd like to emphasize that this gradient is high dimensional, as we take the gradient with respect to the entire field, and the field is a function function in the set of of random surfaces. So this vector matrix product is rather high dimensional, but and it's not obvious how to get rid of this randomness here. But by this Gauss representation, which is a representation of that renormalized potential using a multi-dimensional Fourier ansatz, we get a sufficiently good bounds on this term here, so that we can actually take the supremum over all field configurations, and this is a way of getting rid of this randomness here. So we take the supremum over all fields, and then we have a deterministic object here, and the bounds that we obtain are good enough to integrate this from 0 to infinity, and this allows us to bound this by a deterministic constant. So let me also emphasize that a lot of work is necessary to establish these results, and it's by far not obvious that this can be indeed bounded by a constant, and it really uses the structure of this renormalized potential, and so it is not clear that the same would hold for other models. Okay, so there is two additional statements in this theorem. The first is on the Hölder continuity and on the behavior of this difference term at 0. But these two properties can be seen using similar arguments as we used for this uniform bound. So again, we use the Gauss, the rather explicit Gauss representation, and the strong bounds that we have on the gradient. And finally, this independence here between the small scales of the Gaussian free field and the large scales of the Sine-Gordon field can be seen by expanding these objects and observing that in the first case we have measurability with respect to this sigma algebra, and in the second case it is easy to see that we have measurability with respect to this sigma algebra, and of course these two sigma algebras are independent, which shows that these two fields are independent as well. Okay, let me also so this result was also on the last slide in Roland's talk, and so here these are again the Hölder estimates for this difference field phi delta, and the most important thing here is that we can bound these random quantities on the left hand side by constants which are deterministic and which depend only on the coupling constant z here and the parameter beta. Also, another thing that is important is that these estimates look different depending on how we choose beta. So as Roland mentioned already, so the further we approach this critical parameter beta is equal to 8 pi, the harder it gets to establish these bounds. And our result, so we managed to find these Hölder estimates up to 6 pi, and it is absolutely not clear if similar results can be established beyond this threshold. And this is also the reason why our convergence result only holds up to 6 pi. Okay, so in the last section, in the last two sections, I'd like to explain how we can use this very important coupling result in order to prove convergence in law for the sequence of centered maxima of the Sine-Gordon field. And in the first, so first I want to explain a very important reduction step in which we eliminate the terms that destroyed independence in the case of the decomposed Sine-Gordon field. So here is again the decomposition of this Sine-Gordon field. So we can decompose this field into the small scales and the large scales of the discrete Gaussian free field. And then we have independence between the red and the blue field here. And what is left is just this difference term Rs, which is given by the difference of this difference term phi delta, and which has the following explicit form. Okay, and so the idea is now to get rid of this this additional term Rs and to have an auxiliary field phi s tilde, which has the nice property of independence. And the arguments for this reduction step are somewhat elementary. So the statement is that we can replace this Sine-Gordon field that we were initially interested in by this auxiliary field phi s tilde, in the sense that if we can, so we fix a scale S, and if we can identify the limiting distribution of this auxiliary field, of the maximum of this auxiliary field phi s tilde as a randomly shifted Gumbel distribution, then the same must hold for the limit S to 0, in which case we get the statement for the Sine-Gordon field. So let me highlight the advantages of this new field, of this auxiliary field phi s tilde. So first of all, we have independence, which is a very nice property, independence of small scales and large scales. Second, the field on the small scales actually converges to a smooth field as epsilon, as this regularization parameter epsilon tends to 0. And the non-Gaussian part, remember this is the part which causes the problems, which makes the whole thing more subtle. This is now only isolated in the large scales of the field, but not on the it's not visible on the small scales. So in the small scales we have only this Gaussian part. And the main advantage is now that this decomposition is already very similar to the corresponding proof for the discrete Gaussian free field, which existed already in the literature. And this further allows us to connect to the proof of the discrete Gaussian free field. Okay, so in the last section, I will explain what we actually mean by connecting to the proof of the discrete Gaussian free field. So that the main reference here is this result by Brahms and Ding-Saituni, where they obtained convergence in law for the centered maximum of the discrete Gaussian free field. Okay, and so the first step in this very important paper is the observation that we can use a Gibbs Markov decomposition with respect to a grid gamma. So we take the unit torus and we subdivide the unit torus into k-squared subboxes of psi length 1 over k. And then so the Gibbs Markov decomposition tells us then we can write the discrete Gaussian free field as a collection of independent discrete Gaussian free fields in these boxes. So in every box we have now an independent discrete Gaussian free field plus some independent overall field which has a boundary covariance as epsilon tends to 0. So let me emphasize that this is this collection of Gaussian free fields is called the fine field, and the second field is called the coarse field. And for the coarse field, it's possible to take the limit epsilon to 0, but for the fine field, it's not possible. So in taking epsilon to 0, this coarse field converges to a continuous field whose regularity still depends on the number of boxes. Okay, and the main observation here is that, so when we have a look at this result by Bramson and Saituni, we see that most of the work is actually devoted to results, to prove results that only depend on the fine field. So I say that again, most of the work is devoted to results that only depend on the fine field here. And for instance, such a result is the following proposition. So in this proposition, the limiting behavior, the asymptotics of the probability of the following event are identified, and the asymptotics are here given by the inverse of this fraction. And as I said, a lot of work is necessary to establish these results, and so our strategy is now to make this fine field here appear in the decomposition that we already have for this auxiliary field phi s. Okay, let me briefly summarize what we established so far. So first, initially we were interested in the Sine-Gordon field and the maximum of the Sine-Gordon field, which was given by this process starting at infinity and going down all the way to 0. And then we found that we can replace, so if we're interested in the maximum, we can replace the Sine-Gordon field by the field phi s tilde, by this auxiliary field, which has the following nice decomposition and which has here an independence between large and small scales. And then we learned by looking at the proof of the discrete Gaussian free field that large parts of the proof of this corresponding result only involve the fine field which comes from the Gibbs Markov decomposition. So now, as I said, the strategy is to make this fine field appear in our decomposition, and of course we try to make it appear in the small scales where we already have a Gaussian field. And so this Gaussian field is given by the following stochastic integral. So we integrate only over the small scales, this heat kernel. And the message here is that we can decompose this Gaussian field into two independent Gaussian fields by just choosing the covariance matrices suitably. And so what turns out to be very useful is choosing the covariance matrix of X here to be a massive Gaussian free field, where the mass is given by the initial mass plus 1 over the scale parameter S. And of course, this mass term gets larger once S converges to 0, but this is not important as we fixed S once and for all, and as we first take the limit k to infinity and then S to 0. Okay, and so consequently, the covariance matrix of this additional field X H is given by the following matrix, and so it is not obvious that this is indeed a covariance matrix. In other words, that this is positive definite here, but in fact one can check that. If we look at the left-hand side as a function of the discrete Laplacian, then this function is positive. So the covariance. So this is in fact a covariance matrix. And if we look at this function at infinity, we find that this function has sufficient decay, which allows us to conclude that this field XH is in fact a Hölder continuous field uniform in epsilon. Okay, and now we have in this decomposition a massive discrete Gaussian free field, and this has again a Markov property, so we can use a similar decomposition as in the corresponding proof for the discrete Gaussian free field to further decompose this field X here using the Markov decomposition into a field into the field X Fk, which is now the same as in the corresponding proof for the discrete Gaussian free field plus some independent field which I denoted XSK and this is the analogous field to the coarse field in the Gibbs Markov decomposition. Okay, so overall, this leads to the following decomposition of this auxiliary field phi s tilde. And so we see we have now a decomposition which is very similar to the decomposition in our reference paper. And so the main advantages here, I'd like to emphasize this again on now. First of all, the non-Gaussian part, which is phi s tilde, is only isolated in the coarse field, and moreover, the fine field is now the same as in the corresponding proof of the discrete Gaussian free field. So, and from this point on, the strategy is now as follows. So since we have the same fine field, we can take all the results that has been established for this fine field without further adjustments, and the only work that is now left to do is to generalize all the results which involve the coarse part, and to generalize these results to the case where we have a non-Gaussian field. And this is so even though this is a significant simplification of the problem, it is not obvious that the same steps can still be conducted. And so, for instance, there is still purely Gaussian results which are necessary to establish these steps, such as comparison inequalities for the maximum, which in this case is the Sudakov-Wernicke inequality. But since but here again, this independence of the non-Gaussian part really helps, as we can, for instance, circumvent this problem by not having, this Gaussian comparison inequality, by just conditioning on the non-Gaussian part. In this case, we get a conditional version of, for instance, the Sudakov-Wernicke inequality, which then allows us to generalize the result to this coarse field, which has a non-Gaussian part. Okay, so this is the end of the talk. Thanks a lot for your attention, and yeah, if there's any questions, feel free to ask now, or maybe later if you want. So yeah, thanks a lot for your attention, and thanks.
Thanks, Michael. Any questions?
I will stop sharing. Well, I will leave it on for a second.
Michael, I wanted to ask, maybe this is also for Roland, do these analyses also carry over to the integer valued Gaussian free field, or that is somehow the case that beta is very, very high and is not included?
So I personally haven't looked at the integer value Gaussian free field so far. Maybe Roland, can you add something on?
That is more delicate. I mean, in some sense, in the integer valued Gaussian free field, you're interested in the regime where beta is high, where the field is rough, right? So in both cases, I guess you're interested in the case where the field is rough and looks like a free field in some regime, right?
Right.
In our case, it looks like a free field at small scales, and the integer valued free field, it would look like a free field at large scales. And somehow the issues in controlling the non-Gaussian part, they're a bit different for the small scale and the large scale problem. And so in particular, these strong coupling, the strong coupling we use here will not work as, I mean, it does not work like this in the integer valued free field.
All right. Okay. Very good.
You certainly could not hope for an additive composition of it with an independent Gaussian component. If you want to be...
Sorry?
I'm saying in that case, you cannot hope for an additive decomposition with an independent Gaussian component, because that would not be integer valued.
Indeed. Yeah.
So,
yeah, I was just wondering about the coupling in general and what can be used. All right.
Yeah, I mean, I think that it's just a bit of a different problem. I mean, it's of course also extremely interesting, and yeah, as everyone said, it's not going to be not going to hold in the same way for exactly the reasons that you have the integer value constraint and so on. You can't make that go away.
Thanks.
Any more questions?
Can I ask a question? So in the description of the limit, the random shift, I guess, is coming from all these additions of the coarse field and the coarse Gaussian field and the nonlinear field, etc., etc. Is there some kind of relation between this ZSG and the coarse one for the Gaussian? Is that somehow additive or not at all?
Yeah, in fact, the law of this random variable S set SG is actually given so that I mean that the density with respect to the corresponding random variable for the discrete Gaussian free field is given by e to this difference term. So it is related to the field or to the random variable for the discrete Gaussian free field.
So
maybe you say it's slightly different. I mean, I think it's the same, but so for the free field, in the Gaussian free field, it's given by the total mass of this critical multiplicative, this derivative martingale, right?
Yeah.
Yes.
Which is a measure. And in this case, it should be given by the integral of the derivative martingale with e to the difference field.
But the difference field is dependent on the derivative martingale or not? That's really the question. So
yes,
can
the
you...
difference field does depend. I mean, it does depend on it. But I mean, there's an expression. I don't know. I mean, we didn't check this. I mean, but we have no doubts it's true. But
okay.
It will be given by the integral of the derivative martingale with respect to e to the difference field, and the difference field is uniformly controlled, but it does depend on the derivative martingale.
Yeah, it's not clear because when you take the derivative martingale at the limit, you lose details. So
yeah, I mean, okay. In fact, maybe that's an interesting question. So maybe let me revise my statement and say I mean, it a priori depends on it, but you may well be right that that it actually doesn't. But I mean, we didn't. Okay, we're relatively sure you could check that it can be given by the derivative martingale integrated against this, though we haven't done the details. And then, of course, it is indeed a good question of whether they're independent or not, which I don't have a good feeling for, but you might be right.
I don't know.
Yeah.
No, I'm not offering a conjecture.
But I mean, I guess the summary is relatively concrete. I mean,
yeah, it looked that way. Thanks.
Right. More questions? If not, then let's thank both speakers again.
Thank you very much.
See you all, and see you all next week.
thank you.
Thank you. Bye.
Again for the invitation.
Yeah, thanks for the invitation.